In order to properly apply overcurrent protected devices, you must have a basic understanding of the key fundamental principles in applying such devices. Fusology is the study of these key principles applied to fuses. These include the ratings and operating characteristics that make the fuse an efficient overcurrent protected device, as well as its construction that creates its unique leadership role in circuit protection. Electrical distribution systems can be simple or complicated. However, they cannot be absolutely fail-safe and are subject to destructive overcurrent events such as overloads, ground faults, or short circuits. Harsh environments, general deterioration, damage, excessive electrical system expansion, or overloading are common factors leading to overcurrent events. Reliable overcurrent protected devices prevent or minimize costly damage to transformers, conductors, motors, and many other components that make up a complete power distribution system. Reliable circuit protection is also essential to electrical safety for personnel, as well as avoiding severe monetary losses from power blackouts or prolonged facility downtime. The fuse is a simple and reliable overcurrent protected device that is comprised of a fusible link or links encapsulated in a tube or housing that are connected to terminals. The link's electrical resistance is so low that it acts as a conductor until it encounters current levels above its amp rating. Then it melts and opens the circuit to protect conductors, components, and loads. Fuses for electrical distribution systems typically have these unique performance characteristics that address Frieml's laws of overcurrent protection. First, they have high interrupting ratings to safely open under very high fault currents without rupturing. Second, they are current limiting and limit fault currents to low values for optimum component and equipment protection. In addition, the current limitation helps to achieve high equipment short circuit current ratings. Finally, when applied with the correct amp ratios, fuses can easily be selectively coordinated for the full range of overcurrent events to help prevent unnecessary blackouts. Let's further examine Frieml's laws of overcurrent protection. While these laws are not all inclusive of the considerations in applying overcurrent protected devices, an understanding of these key concepts will lead to a safer, more reliable, and code-compliant electrical system. Frieml's first law of overcurrent protection addresses interrupting rating. It states overcurrent protected devices shall be applied with an interrupting rating equal to or greater than the maximum available fault current. Why is this important? It's about safety and the ability for overcurrent protected devices to safely interrupt the fault. This also helps to comply with NEC 110.9, which requires the interrupting rating to be equal to or greater than the maximum available fault current. Of overcurrent protection tackles component protection. It requires overcurrent protected devices be selected and installed to clear a fault without extensive damage to electrical equipment and components. This is critical for the reliability and safety of the electrical system. It also addresses and helps meet NEC 110.10 and various other code articles related to short circuit current rating. Finally, Frieml's third law of overcurrent protection states that a properly engineered and installed electrical system will restrict outages to only the nearest upstream overcurrent protected device for the full range of overcurrents and associated opening times, leaving the remainder of the system undisturbed and preserving system continuity. Numerous NEC sections now require selective coordination for critical systems, such as elevators, emergency systems, legally required standby systems, critical operations power systems, and more. Reliability and safety are paramount in these systems and are a key factor in selecting the overcurrent protected device. The purpose of the fuse is to act as electricity safety valve to protect equipment and components from all types of overcurrents, thereby minimizing damage. An overcurrent is either an overload, a short circuit, or a ground fault. The overload current is an excessive current relative to normal operating current, but still confined to the normal circuit path provided by the conductors, components, and loads, whereas a short circuit or ground fault flows outside the normal circuit path. Overloads are most often between 135% and 6 times the normal current level. Persistent, non-temporary overloads can result from defective motors with worn bearings or too many loads on a single circuit. It must not be permitted to last long enough to damage electrical system components. This damage may eventually lead to more severe events if the overload is not interrupted. Due to the overload's inherent low magnitude nature, removing them within seconds or even minutes will generally prevent thermal damage. Short circuits differ from overloads as they can be hundreds to thousands of times greater than the normal operating current. A high-level short circuit may be up to 30,000 or even 200,000 amps and must be interrupted as quickly as possible to minimize damage. This could include high magnetic forces that warp and distort bus bars and associated bracing beyond repair, severe insulation damage, melting or vaporizing conductors, vaporizing metal, including buswork and electrical equipment, ionizing gases, arcing fires, and explosions. An understanding of what happens during a short circuit is important to properly apply equipment and protective devices. Here is a diagram representing a worst-case single-phase waveform for the first few cycles. This condition is characterized as a volted three-phase fault, where all phases are connected together. This results in the maximum thermal and mechanical stresses in the system. The short circuit current takes on an asymmetrical characteristic during these first few cycles until it becomes symmetrical. It is important to concentrate on what happens during the first half cycle after the initiation of the fault. The asymmetry or magnitude of the first peak is a function of the X/R ratio or total resistance and reactance in the system. To calculate the worst case asymmetrical peak, assuming 50,000 amps RMS symmetrical, available at a 15% power factor or X/R ratio of 6.6, 50,000 amps would be multiplied by 2.3 to equal approximately 115,000 amps asymmetrical peak. It is important to note that short circuit calculations in a system are performed without any overcurrent protective devices, such as fuses or circuit breakers in the system. Calculations are completed assuming copper bus bars are replacing these devices to determine the maximum available fault current at various points in the system. Only then should the effect of the protective device be analyzed. Calculations should be made at various points in the electrical system, including service entrance, panel boards, switchboards, motor control centers, disconnects, load centers, transfer switches, industrial control panels, and machines. A quick and simple method to determine the available fault current is to use the Eaton-Bussmann series fault current calculator, available on the App Store or Google Play. It is also available for online use as a free tool to calculate fault currents based on the voltage, transformer size, impedance, and conductor length. Fault current calculations in the palm of your hand. The fuse is a highly efficient overcurrent protective device with a simple design based upon principles of physics to interrupt and limit overcurrent events. Fuses have 4 parts common to most designs: the tube or cartridge, terminals, blades or ferrules, the fuse link or element, and arc quenching filler material. Many different sizes and types exist for various applications. The unique construction of the fuse offers several benefits. Fuses have rejection features based on physical size or by a construction characteristic. A fuse of one class and case size cannot be installed in a different type of mounting. This ensures that the replacement fuse being installed will have the same voltage and interrupting ratings. One exception is that Class R fuses can be installed in Class H fuse mountings, offering an upgrade in protection. However, lower performing Class H fuses cannot be installed in Class R fuse holders. The Class J fuse is size rejecting and virtually eliminates installing the wrong fuse type with potentially lower performance characteristics. Fuses do not vent when they interrupt fault currents. All arcing is contained and extinguished inside the fuse body. This reduces the risk of metal vapors causing unnecessary damage to other components inside an enclosure. Modern current limiting fuses are constructed with an enclosed case tube or body and have no moving parts when interrupting fault currents. By operating on thermal energy principles of physics, the fuse improves electrical system reliability by not relying on springs, levers, or latches that require periodic maintenance to ensure continued proper operation. Fuses are factory calibrated devices that do not require any adjustments or settings in the field. This minimizes possible misapplication of the device, and engineers can be certain the level of protection specified is met and retained. Depending upon the amp rating, the fuse may have one or more fuse elements. These elements are electrically connected to the terminals and enclosed in the tube that contains an arc-quenching filler material surrounding the element. Many Bussmann series Limitron fuses are single-element fuses. Under normal operation, when the fuse is applied at or near its amp rating, it simply functions as a conductor. If an overload occurs and persists for more than a short time interval, the element temperature eventually reaches a level that causes a restricted link segment to melt. As a result, a gap is formed and an electric arc established. The arc's resistance eventually reaches such a high level that it cannot be sustained and is extinguished. Present-day single-element fuse designs respond very quickly to overcurrents with excellent fault current component protection. However, temporary, harmless inrush currents associated with inductive loads, such as motors and transformers, may cause nuisance openings unless oversized. Therefore, they are best used in resistive circuits not subjected to inrush currents. Subjected to fault currents of 30,000 amps or higher, the fuse's current limiting response is extremely fast, as its restricted link sections will simultaneously melt. The multiple arcs' high total resistance, together with the arc-quenching filler material, results in rapid arc suppression, and clearing the fault typically takes less than a quarter cycle or 4 milliseconds. Unlike single-element fuses, Bussmann series dual-element fuses feature two unique elements, one for overloads and another for short-circuit operation. The overload element provides intentional time delay to permit harmless temporary inrush currents to pass without nuisance operation. These fuses can be sized closer to the load to provide high performance for both short-circuit and overload protection. The short-circuit element handles fault currents, and when operating in its current limiting range, it's not possible for the full available fault current to flow through the fuse. It's a matter of physics. The small restricted link sections in the short circuit element quickly vaporize with the filler material assisting in forcing the current to zero. Therefore, it's able to limit the fault current. Upon closer examination of the dual element fuse link, we can see the two separate elements for overloads and short circuits connected in series. The filler material fills a tube surrounding the short circuit element for superior arc quenching. Operation under persistent overload conditions causes the trigger spring to fracture the calibrated fusing alloy and releases the connector. The coiled spring pushes the connector from the short circuit element and the circuit is interrupted. For fault conditions, the short circuit element is designed with minimum metal in the restricted portions to greatly enhance the fuse's current limitation and minimize the let-through current. Fault current causes the short circuit element's restricted portions to quickly vaporize and commence arcing. The arcs burn back the element, resulting in longer arcs that reduce the current. This is aided by the arc-quenching filler, forcing the current to zero. The very fine arc-quenching material plays an important role in the interruption process, as it assists in quenching the arc by absorbing their thermal energy and forming an insulating barrier called fulgurite. And that's it. Simple, reliable, and current limiting. All fuses have three basic ratings that must be understood and are crucial to specifying and applying the correct circuit protection. These are voltage, current or amp rating, and interrupting rating. Proper application requires the overcurrent protected device's voltage rating be equal to or greater than the system voltage. When an overcurrent protected device is applied beyond its voltage rating, there may not be an initial indication that anything is wrong. But when it attempts to interrupt an overcurrent, adverse consequences can result and may self-destruct in an unsafe manner. There are two overcurrent protected device voltage rating types, straight voltage rated and slash voltage rated. A straight voltage rated device can be installed in any electrical system regardless of the grounding system. All fuses are straight voltage rated and their proper application is straightforward. These devices have been evaluated for proper performance with full phase-to-phase voltage. The fuse's voltage rating must be at least equal to or greater than the circuit voltage. For example, a 600 volt rated fuse can be used in a 208 volt circuit, but a 250 volt rated fuse cannot be used in a 480 volt circuit. Most low voltage power distribution fuses have 250 volt or 600 volt ratings. Bussmann series low peak LPJ fuses are rated at 600 volts and can be used on any system 600 volts or less, whether it's solidly grounded, ungrounded, impedance grounded, or corner grounded delta. A straight rated fuse or circuit breaker can be used to protect single-phase line to neutral loads when supplied from a three-phase, solidly grounded circuit. For example, a 300 volt rated fuse can be used to protect single-phase line to neutral loads when supplied from a three-phase, solidly grounded 480-277 volt circuit, where the single-phase line to neutral voltage is 277 volts. This is allowed in this application because a 300 volt fuse will not have to interrupt a voltage greater than its 300 volt rating. Slash voltage rated overcurrent protected devices have limitations imposed upon them that straight rated voltage overcurrent protected devices do not. Multiple pole mechanical overcurrent protected devices with a slash voltage rating, such as circuit breakers, self-protected starters, and manual motor controllers, are limited in their application and require extra evaluation for use. The slash rating can be broken down into its higher and lower numbers. The lower rating pertains to overcurrents at line to ground voltages, intended to be cleared by one pole of the device. The higher rating number pertains to overcurrents at line to line voltage, intended to be cleared by 2 or 3 poles of the device. The proper slash rated circuit breaker application is such that the line to ground voltage does not exceed the device's lower voltage rating, and the line-to-line voltage between any two conductors does not exceed the device's higher voltage rating. Understanding the higher and lower ratings is important, as slash-rated devices' misapplication can result in it being applied outside its voltage rating, with dire consequences should the device be called upon to interrupt overcurrents. The amp rating of the overcurrent protected device indicates the amount of current that can flow through the device without causing it to open. In many cases, the fuses are sized per NEC requirements, and the next standard size must be used per NEC section 240.6. In selecting the amp rating, consideration must be given to the load type and code requirements. The fuse amp rating normally should not exceed the circuit's conductor current carrying capacity that's determined by ampacity adjustment factors covering how and where it's routed or other NEC-related areas. For the most part, if a conductor's current carrying capacity is 20 amps, a 20 amp fuse is the largest it should be used to protect it. There are specific circumstances in which the amp rating is permitted to be greater than the circuit's current carrying capacity, such as in motor circuits. Dual element time delay fuses are permitted to be sized up to 175%, and non-time delay fuses up to 300% of the motor's full load current. As a rule, the fuse amp rating should be selected at no closer than 125% of the continuous motor load current. There are exceptions, such as when the fuse switch combination is approved for continuous operation at 100% of its rating. The third, and arguably the most critical, if not most misunderstood rating, is the interrupting rating. Overcurrent protected devices must be able to safely interrupt destructive fault current energy. If a fault current exceeds a level beyond the device's capability, it may rupture, causing damage and posing a serious safety hazard. The rating that defines the overcurrent protected device's ability to maintain its integrity is called its interrupting rating. It's important when applying a fuse or circuit breaker to use one that can safely interrupt the largest potential fault currents. Most modern current limiting fuses have a 200 kA or 300 kA interrupting rating and can be used in just about any system without fear of misapplication. The National Electrical Code in Section 110.9 requires equipment intended to break current at fault levels to have an interrupting rating sufficient for the available fault current. The fuse interrupting rating is not dependent on a particular voltage when applied within its rating. For example, a 600 volt rated LPJ fuse has a UL listed 300 kA interrupting rating for any voltage up to 600 volt AC. Whether for the initial installation or system updates, a fusible system can maintain a sufficient interrupting rating throughout its life. There is little need for additional fault current calculation or worry that the fuse will be misapplied due to an improper interrupting rating. Nor is a short circuit study needed when applying Bussmann series dual element time delay low peak fuses for selective coordination, so meeting NEC requirements is easy. Additionally, high interrupting ratings help equipment achieve a high short circuit current rating that may be limited by a device with a low interrupting rating. When applying a fuse or a circuit breaker, the device must be able to safely interrupt the largest available fault currents at its aligned terminals. The following test shots will demonstrate the destructive nature of short circuit events and the importance of proper interrupting rating. These tests will be conducted on a 480 volt circuit with an available fault current of 50,000 amps. It is not the intent to degrade any equipment, but rather show the possible result of misapplication of the equipment used. The first test will show two 600 volt general purpose fuses with a 10,000 amp interrupting rating. A short circuit is applied directly on the load side of the fuses. Notice the large destructive forces released during the test. This presents a serious safety hazard and misapplication. The next test shows a higher rated circuit breaker on the same test circuit with a short circuit directly on the load side of the two-pole device. In this case, the circuit breaker is listed to interrupt 14,000 amps. Again, notice the extreme thermal and magnetic force of this event. Molten metal and shrapnel pose serious safety hazards to electricians, maintenance personnel, and anyone that may be nearby. The final test is not as exciting, but it is very important to demonstrate the proper application of overcurrent protective devices when it pertains to interrupting fault current. Again, the test circuit is the same, capable of delivering 50,000 amps of fault current, but in this case, the fuses protecting the circuit are Bussmann series low peak, dual element, time delay LPJ fuses with a 300,000 amp interrupting rating. Notice how the fault was cleared safely and without violence. As depicted in these tests, it is absolutely necessary to determine the available fault current at the line side terminals of each overcurrent protected device. The advantage of high 200 kA or 300 kA fuse interrupting ratings is that they can be applied and used to eliminate the need for fault current calculations, as these high interrupting ratings will exceed the available fault currents for virtually all power distribution systems. Eaton's Bussmann series low peak fuses are the only fuses tested and listed by UL to 300,000 amps. This high interrupting rating is capable of safely interrupting virtually any available fault current encountered in a 600 volt or less system. The 300 kA interrupting rating provides assurance that when a properly sized low peak fuse is installed, the system is covered for the worst case overcurrent event. The National Electrical Code defines a branch circuit overcurrent protected device as one that is capable of providing protection for service, feeder, and branch circuits and equipment over the full range of overcurrents between its rated current and its interrupting rating. They are also the only overcurrent protected devices the NEC permits to be installed in a building's electrical system. In addition, such devices must have interrupting ratings appropriate for their intended use, but no less than 5,000 amps. Branch circuit devices can protect branch and feeder circuits and service conductors at any point in the electrical system. In addition, the interrupting rating must also comply with Article 110.9. Shown here are the UL248 listed fuses along with UL49 molded case circuit breakers and UL1066 insulated case and power circuit breakers that provide acceptable branch circuit protection. The UL248 fuse standards cover distinct low voltage fuse classes below 600 volts AC. Of these, modern current limiting fuse classes CC, CF, G, J, L, R, and T are the most important. The branch circuit current limiting fuses rejection feature helps ensure electrical system safety over its life because it prevents installing other fuse classes of larger case sizes. Fuses that cannot provide a comparable minimum protection level for critical ratings and performance cannot be inadvertently installed. This is inherent in all current limiting fuse classes. Each fuse class must meet maximum let-through limits during fault conditions, minimum voltage ratings, minimum 200,000 amp interrupting ratings for class CC, CF, J, L, R, and T, physical rejection of different fuse classes and case sizes, and non-current limiting fuses. These product standards ensure branch circuit fuses provide specific minimum circuit protection when current limiting fuses and equipment are used. A given fuse class will ensure the voltage and interrupting rating and degree of current limitation for the electrical system's life. An example is in Class J fusible equipment. Only Class J fuses can be installed. This ensures the voltage rating is always 600 volts, the interrupting rating is at least 200,000 amps, and the fault current protection is provided by its current limiting let-through characteristics. If the fuse needs replacing, only a Class J fuse can be installed. For more information on branch circuit fuse types and classes, see the Bussmann Series Fusology Technical Guide or the Bussmann Series Full Line Catalog. In contrast to the branch circuit fuses, supplemental fuses and other application-limited overcurrent protected devices cannot be used in a building electrical system. These include supplemental fuses listed to UL248, supplemental protectors, and motor circuit protectors. These devices are limited in their application and could cause a serious safety hazard if misapplied. These application-limited devices have limited agency listing and use, limited voltage ratings and interrupting ratings, and varying construction and performance characteristics. For these reasons, it is important to not let their lower price sway decision-making while sacrificing safety and performance. Time current characteristic curves, or simply time current curves, are graphical representations of fuse operation under different overcurrent conditions as plotted by amps and time. These curves also provide a visual means for comparing overcurrent protected devices against one another for purposes of selective coordination analysis. This curve shows the time current curve for a 400 and 100 amp dual element time delay fuse in series as depicted in the one-line diagram. The graph's horizontal axis represents the RMS symmetrical current in amps. The vertical axis represents the time in seconds. Each fuse is represented by a band comprised of the minimum melt characteristic. The solid blue line shows the lower operating characteristics, and the hashed red line illustrates the total clearing characteristics. The area between these two lines represents the band that under specific test conditions will melt the fuse element, arc, and clear the circuit. Time current curves for fuses are primarily used to understand the opening time duration during overload or long time conditions. Fuses have an inverse time current characteristic, meaning the greater the overcurrent, the faster the fuse opens and interrupts. For example, a 100 amp fuse subjected to a 200 amp overcurrent will open and clear in approximately 200 seconds. However, for an overcurrent of 1000 amps, the 100 amp fuse will open in approximately 1.75 seconds, shown as point D. And for a 2000 amp overcurrent, the time current curve tells us it will open and clear in approximately 0.17 seconds. This will all be well before the time it takes the 400 amp fuse to even begin to melt. For overcurrents up to approximately 11,000 amps, shown at point H on the graph, it can be determined that these two fuses selectively coordinate, since there isn't any overlap on the curves, and the current is less than where the 400 amp upstream fuse crosses 0.01 seconds. When overcurrents exceed this value, selective coordination cannot be determined by using time current curves alone. Fuse selectivity ratio tables must be consulted. Using the Bussmann series fuse selectivity ratio table makes it simple to determine whether fuses selectively coordinate and eliminates the need for plotting time current curves. While important, selecting overcurrent protected devices based solely on their ability to carry system load current and interrupting the maximum fault current at their respective application points is not enough. As the demand for power system reliability increases, the overcurrent protected device's performance becomes more critical, as its function should ideally limit system outage to only that portion of the circuit which is faulted. The selected overcurrent protected device types and ratings determine whether they are selectively coordinated upstream, such that only the nearest upstream device will open for the full range of overcurrents and opening times. This leaves the remainder of the system undisturbed to preserve service continuity. Here we can see the minimum amp rating ratios for Eaton's Bussmann series low peak fuses required to provide selective coordination between upstream and downstream fuses. It's a simple matter to selectively coordinate a system using published fuse amp rating ratio tables and maintaining the minimum ratio between an upstream and downstream fuse. This will ensure selective coordination is achieved for all fault currents up to the fuse's interrupting rating. The fuse selectivity ratios can be found in the selectivity ratio table in the Bussmann Series Fuseology Technical Guide or the Bussmann Series Electrical Protection Handbook, SPD. The National Electrical Code requires selective coordination for critical loads on specific systems, including elevator circuits, campus-style fire pumps, emergency systems, legally required standby systems, and critical operations power systems. The NEC defines selective coordination as restricting the outage to only the circuit affected for the full range of available overcurrents and for the full range of opening times associated with those overcurrents. The fault current must be known and considered in the analysis for selective coordination. Current limitation is a function of how quickly the fuse can react to a fault and clear it before the fault current can build up to destructive levels. NEC 240.2 defines a current limiting device as a device that, when interrupting currents in its current limiting range, reduces the current flowing in the faulted circuit to a magnitude substantially less than that obtainable in the same circuit if the device were replaced with a solid conductor having comparable impedance. Fuses that limit the let-through current to downstream components provide protection from thermal and magnetic forces while providing numerous benefits. Current limiting fuses enhance workplace safety by reducing the incident energy personnel are exposed to under fault conditions. Arc flash hazards may be greatly reduced when compared to using a non-current limiting overcurrent protected device, especially at 600 amps and below. Fuses can protect components and equipment from extreme thermal and magnetic forces by clearing the fault current within the first half or quarter cycle. Conductors, busway, motor starters, switches, and other devices can be well protected with current limiting fuses. Fuse current limitation helps equipment achieve high short circuit current ratings. Branch circuit components inside industrial control panels and machines, HVAC control panels, and other UL 508A listed equipment can be protected by current limiting fuses in the feeder circuit. The low peak let-through can help raise the overall equipment short circuit current rating, even with lower rated devices in the branch circuit, as long as the peak let-through current is less than the branch circuit component's short circuit current rating and the branch circuit overcurrent protected device's interrupting rating is sufficient. Current limitation is a key part of selective coordination, and current limiting fuses save the engineer or designer time and money by reducing the need for a selective coordination study, as long as the minimum amp ratio is maintained between upstream and downstream fuses, such as a 2:1 amp rating ratio for Bussmann series low peak fuses. Selective coordination is achieved and unnecessary power loss to upstream circuits is prevented to any fault current up to the interrupting rating of the fuse. Protecting electrical system components from fault currents is critical when selecting overcurrent protected devices. The engineer or specifier should consider the electrical circuit components SCCR, such as wire, bus, or motor starters, and whether proper circuit protection will improve reliability and reduce the possibility of injury. Electrical systems can be destroyed if overcurrent protected devices do not limit the fault current to within the system's component short circuit current rating. Merely matching the component amp rating with the protected device amp rating does not ensure component protection under fault conditions. A non-current limiting overcurrent protected device permits fault current to build up to its full value and lets through an immense amount of destructive current, heat, and magnetic energy before opening. Some overcurrent protected devices will permit short circuit currents to flow for more than one cycle. The shaded area under the curve represents the energy being dissipated in the circuit, with both magnetic forces and thermal energy being directly proportional to the square of the current, making it important to limit the short circuit current to as small a value as possible. The maximum magnetic forces vary as the square of the peak current, and the thermal energy varies as the square of the RMS current. This waveform demonstrates this same short circuit when the fuse operates within its current limiting range. A current limiting fuse has such a fast response speed that it cuts off the current long before it can build up to its full peak value. In the first major fault current cycle depicted by the waveform, a non-current limiting overcurrent protected device would let through approximately 100 times as much destructive energy as a current limiting fuse. This is assuming an asymmetrical peak current of 100,000 amps and a peak let-through current of 10,000 amps. Modern fuse designs are current limiting and greatly reduce a fault current's destructive peak and duration to protect downstream equipment. This can reduce the bracing needs for bus structures and minimize the need for components to have high short circuit current ratings or withstand ratings. If not limited, destructive faults can reach levels of 30,000 amps or higher, even up to 200,000 amps in the first half cycle, which is approximately 8 milliseconds. The immense heat that can be produced in circuit components can cause conductor insulation damage or violent component explosions. At the same time, huge magnetic forces developed between conductors can crack insulators and destroy bracing structures, with the maximum mechanical force exerted being proportional to the square of the instantaneous peak current. It is extremely important that overcurrent protected devices limit fault currents before they reach their full potential. The cable whip test visually illustrates the difference between current limiting and non-current limiting overcurrent protected devices. These tests were conducted at 40 volts with 90 feet of 2-aught conductor placed on the lab floor. The available fault current is calibrated to 26,000 amps symmetrical. The first test uses a non-current limiting protected device with a 1-cycle clearing time. This test visually shows the destructive forces associated with fault current. Extreme magnetic or mechanical forces can be seen during this test. However, a 200 amp non-current limiting protected device used to protect this 2-aught conductor would be properly sized per the National Electrical Code. Proper bracing, support, and torque are needed to keep this conductor from pulling out from its terminations and causing additional safety hazards. In this test, the peak current let through was 48,000 amps, with a clearing time of 1 cycle or 16 milliseconds. The next test shows the same conductor but with a 200 amp class RK1 current limiting fuse upstream. You can imagine what the results would look like. Don't blink or you might miss the action. In this test, we see a significant reduction in the let-through energy by the 200 amp Bussmann series low peak fuse. The peak let-through was measured at 10,000 amps, clearing in approximately 4 milliseconds. Since the mechanical forces exerted on this electrical equipment are directly proportional to the instantaneous peak current squared, the current limiting fuse reduced the maximum mechanical force let through by over 95% as shown in this equation. The thermal energy from RMS current flow is not seen in these tests, but was documented in the lab instrumentation. The excessively high fault current flow for a period of time can degrade electrical insulation properties, or the metal can be annealed, melted, or vaporized. The results from this lab test showed the reduction in thermal energy, known as I²T, to be 1/123rd compared to the non-current limiting test. The degree of current limitation of a particular fuse depends on the available fault current that can be delivered by the electrical system. This is shown for each fuse in the fuse let-through curves. The curves are plotted from actual test data in a circuit with a short circuit power factor of 15% or an X/R ratio of 6.6. This establishes the AB line. The fuse curves represent the cutoff value of the prospective available fault current under the given circuit conditions. It is important to understand how the curves are generated and what circuit parameters affect the let-through curve data. The 3 circuit parameters that affect the fuse let-through performance for a given available fault current are the power factor, closing angle, and the voltage. Current limiting fuse let-through curves are generated under worst-case conditions based on these parameters. The benefit: a conservative let-through value for both peak current and RMS current. Under actual field conditions, changing any one or a combination of these will result in lower let-through currents. This provides for an additional degree of reliability when applying fuses for equipment protection. Prior to using let-through curves, it must be determined what let-through data is pertinent to equipment SCCRs or withstand ratings. Equipment SCCR is simply how much fault current the equipment can handle or withstand, and for how long. The most important data obtained from the fuse let-through curves and their physical effects are identified in this example. The peak available fault current is shown as point C. The RMS available fault current is shown as point A. The peak let-through current or mechanical forces is shown as point D. The apparent prospective RMS symmetrical let-through current or heating effect is shown in point B. The clearing time of less than 1/2 cycle when the fuse is in its current limiting range is shown where the fuse curve intersects the AB line. Let's go through a real-world example with an 800 amp circuit and an 800 amp KRPC Class L current limiting time delay fuse with 86,000 amp symmetrical fault current available. To determine the peak let-through current, find 86,000 amps on the x-axis and draw a line vertically until the 800 amp fuse curve is intersected. Then follow this horizontally to the instantaneous peak let-through on the y-axis. This value is 49,000 amps. Had a fuse not been used, the peak current would have been 198,000 amps. To find the apparent prospective RMS let-through current, we use what is referred to as the up, over, and down method. First, enter the curve on the x-axis at 86,000 amps. Then proceed vertically to intersect the 800 amp fuse curve. Then follow horizontally or over to the AB line, then back down to the x-axis to find the RMS let-through value of 21,000 amps for this example. Current limitation plays a major role when protecting components and achieving a high short-circuit current rating. Electrical components, such as contactors or motor starters, have a standard fault rating or default short circuit current rating, and sometimes a higher rating called a high fault rating. This high fault rating requires a specific class of fuse and max amp rating to achieve the higher level of protection. An example is this contactor with a 5,000 amp default short circuit current rating. However, this same contactor has a 100,000 amp short circuit current rating when protected by a max 20 amp Class J fuse due to its current limitation. It is a serious safety hazard and misapplication to apply devices beyond their short circuit current rating. Let's take a look at what can happen. Here we have an enclosure with a contactor rated 5,000 amps protected by a non-current limiting overcurrent protected device. This enclosure can only be applied in a system that can deliver no more than 5,000 amps of fault current. But what happens if it sees 65,000 amps? You can see the shock, fire, and projectile hazards external to the equipment. The enclosure could become energized or conductors loosened from terminals. The explosive power of the internal devices failing causes the door to blow apart, exposing fire hazards. Finally, projectile hazards can be seen from the door blowing off and possibly exposing other shrapnel. Providing and specifying equipment with short circuit current ratings equal to or greater than the available fault current will not only comply with the National Electrical Code, but will help provide a safer, more reliable electrical installation. Current limiting fuses can help achieve these higher ratings due to their current limiting characteristics. Overcurrent protected devices play a significant role in electrical safety. Extensive tests and analysis have shown that the magnitude of energy released during an arcing fault is related to two key factors: the time it takes the protected device to open and the amount of fault current the protected device lets through. The faster the overcurrent protected device clears the fault, the less energy is released. If the protected device also limits the current and reduces the actual fault current that flows through the arc, the lower the energy released. Lower levels of energy released means safer working conditions for the worker and better equipment protection. The unique aspect of an arcing fault is that the current flows through air as opposed to through conductors. The product of fault current and arc voltage concentrated at one point results in tremendous explosive energy. High temperatures cause copper to rapidly expand and vaporize, causing extreme thermal energy. Molten metal is blown out, which can cause severe burns and ignite flammable clothing. Blast pressure from the vaporization of metal and superheating air is high enough to rupture eardrums, fracture ribs, and collapse lungs. An arc flash event is very serious. In this test, an arc fault is initiated with a small piece of 10-gauge copper wire wrapped around 3 1-inch copper anodes inside a 20-inch metal enclosure. The available volted 3-phase fault current is 22,000 amps at 40 volts. The fault current is cut off after 25 cycles, or approximately 4/10 of a second, or 400 milliseconds. As this clearly demonstrates, this is a tremendous amount of energy, and unless properly mitigated or protected, could seriously injure workers and damage equipment beyond repair. Now let's run the same test again, but protect the circuit with a 600 amp Mussmann series low peak LPJ fuse. All other parameters remain the same, but the current will be limited by the fast response of the low peak fuse. In this case, the 600 amp LPJ fuse limited the RMS current let through to a value near 10,000 amps, all within the first half cycle, less than 8 milliseconds. Arcing faults can release extreme amounts of energy and destroy equipment and put workers in very unsafe situations. The overcurrent protected device characteristics play an important role in this outcome. Current limiting overcurrent protected devices, such as low peak fuses, when operating in their current limiting range, not only reduce the peak current, but also reduce the time duration current is allowed to flow, thereby potentially reducing the hazards. Current limiting devices may not entirely mitigate the potential hazards, especially when the device is 1200 amps or greater and the available fault current is low. NFPA 70E, the standard for electrical safety, should be consulted, and proper workplace safety practices should always be followed. The arc flash hazard can be identified per NFPA 70E section 130.5E for the arc flash boundary and 130.5G using the instant energy analysis method. The information provided uses the simplified fuse formulas based on IEEE 1584 Guide for Arc Flash Hazard Analysis, and also found in NFPA 70 Annex D. These formulas were derived from actual test data using Bussmann series low-peak fuses. The first step is to determine the available fault current on the line side terminals of the equipment that will be exposed. Second is to identify the upstream low-peak fuse that is protecting that equipment. A table as shown here can then be used to identify the incident energy level exposure expressed in calories per centimeter squared, and the arc flash boundary that will require personal protective equipment based on this energy level. The personal protective equipment should be selected based on NFPA 70E Table 130.5G. This table can be found in the Bussmann Series Fusology Technical Guide. Refer to the notes in this publication in applying these tables and all practices in NFPA 70E before performing any energized electrical work. Let's review some of the features and benefits that make modern current limiting fuses reliable and efficient over current protected devices. Fuses have very high interrupting ratings, up to 300,000 amps, offering many benefits. It provides flexibility for use in any system with available fault currents up to 300 kA, without fear of misapplication to NEC 110.9. In addition, this offers a no-worry solution in case system changes, such as the utility transformer or equipment relocation, results in higher available fault currents. Time is saved by eliminating the need for fault current studies when using 300 kA interrupting rating low-peak fuses. Also, high interrupting ratings help achieve high assembly short-circuit current ratings, as the fuse will not be the limiting factor. Modern fuse designs are current limiting. This helps enhance workplace safety by reducing the incident energy and arc flash hazards personnel may be exposed to under fault conditions. It protects components and equipment from extreme thermal and mechanical forces associated with a fault event. This helps with compliance to NEC 110.10 by protecting equipment and components from extensive fault current damage when properly sized. In addition, current limitation helps achieve high equipment short-circuit current ratings by drastically reducing peak let-through current and protecting downstream low-rated devices. And finally, no damage Type 2 protection can be achieved with properly sized current limiting fuses, reducing downtime and improving overall system protection. The physical rejection feature of current limiting fuses helps provide a safe and reliable system by ensuring the same fuse class with the same voltage and interrupting rating is installed. This reduces the risk that the wrong fuse type with different performance characteristics and lower interrupting ratings could be installed and compromise the protection level. Fuses are constructed with an enclosed tube or body with an internal arc quenching means. They contain no moving parts when interrupting fault currents and do not vent outside of the fuse body. This prevents any collateral damage to other components when interrupting faults and eliminates the need for other barriers or safeguards from such venting. This unique design does not rely on any springs, levers, or latches to open the circuit and therefore provides very reliable circuit protection for many years, eliminating the need for device maintenance or calibration. This also minimizes the possible misapplication and confusion by eliminating the need to adjust or change device settings in the field. Fuses are not resettable, and when replaced with a new factory calibrated device, It's inserted in the circuit. This improves the system reliability throughout its life by ensuring the same protection level is installed after the fault. System integrity is maintained as replacement fuses utilize the latest design and performance improvements. In addition, factory calibrated replacement fuses help to comply with OSHA 1910.334b2 by eliminating the invitation for an operator to reset a device after a fault without first determining the cause. Remember, resetting circuit breakers or replacing fuses in a circuit after a fault without first investigating the cause is prohibited by federal law. Fuses are straight voltage rated and provide flexibility to be installed in any system regardless of its grounding scheme. A slash voltage rated overcurrent protected device is limited to installation in only a solidly grounded Y system. Modern current limiting fuses, such as the Bussmann Series Cube Fuse, are finger safe. When used with the compact circuit protector and in the QuickSpec coordination panel board with door-and-door construction, risk of electric shock is minimized by reducing exposure to live parts when replacing the fuse. Fuse design and innovation have come a long way since the first fuses were simply a smaller piece of wire attached to two terminals meant to vaporize during an overcurrent event. Reliable circuit protection is essential, and modern fuse designs provide the unique features to help reduce downtime, prevent blackouts, and maximize system protection.